I'll present about the pymcabc software, which is a particle physics toy toolbox for the ABC model. And here are the links to the code as well as the documentation of this particular software and its use. So in this talk, I'll present about the ABC model of particle physics. Then I'll also discuss some of the features and the use of pymcabc software. And finally, we'll apply this software for evaluating a line shape of a heavy scalar mediator. So the ABC model, the main motivation for the ABC model is that it simplifies our understanding of the Feynman diagrams, matrix element, that is the dynamics of a physics process. Tree-level results can also be cross-checked by pencil and paper, making it very useful in educational purposes, especially at the undergraduate level. The features of the ABC model, that it consists of 3 scalar particles, and the interaction is only possible when all the 3 particles are present at the interaction vertex. And this model is also useful not just for Feynman, for explaining QFT ideas such as Feynman diagrams, but for regularization or renormalization can also be illustrated with this model. So the Lagrangian of this model is given as this, and as we can see that if each particle were free, it would follow the Klein-Gordon equation. The interaction term is given as here. So now coming to the software, this software is designed such that it can evaluate the differential as well as the total cross-section and the decay widths of any leading order process in the ABC model. Once a process is defined, it can also generate the related Feynman diagrams. It simulates the scattering processes and the decay. If there is a heavy particle in the final state, it can generate a decay. It's possible to get 2, 3, or 4 final state particles that way. It can also apply toy detector effects, assuming that it assumes that there's separate resolution for momentum and energy measurements. Then, even though it is not physical in quantum mechanics, but it is possible in this software to just get individual S channel, T channel, and U channel contributions for educational purposes that I'll discuss in this presentation later. And so the output is in the CSV and the root format, and the analysis is supported therefore in the pandas, uproot, pyroot, root. And all of these analysis examples are given in the main documentation, where simple examples for analyzing is given. And it requires minimum user interaction. And so it can be installed with, it is available from PyPy, and it can be installed using pip install pymcabc. So as the first example, we consider the simulation of the scattering process where A, C are scattered, and in the final state we have the same AC particle, and this interaction is intermediated by the B star, which is B particle B, but it is virtual. So first we import the package. Now we define the physics process. So in this case, we have to simulate AC to AC. So we just define it as this. We need to define the model parameters, which are the masses of the particles and the initial momentum at which this interaction is taking place. We need not define the coupling constant, as at the moment it is set constant to 1. Once this process is defined, we can obtain the Feynman diagrams related to this process. So this is the decay process. Since A is the heavy particle in the final state, we can have a decay process. This is the S channel process, and this is the T channel process. Now, once we have that, we can evaluate the cross-section of the process, and we can get this cross-section. The second quantity is the error on the cross-section. Finally, we can simulate this process where we have 2 options. We can either decay the final state particle, which is A in this case, or we can set it to false. Then we have the option also to apply detector effects or not, but in this case I have applied both of them. And I've just generated 100 events at the moment, but you can, it works for many. And then we can also convert this to CSV output. So the output is root, but we can convert it to CSV as well. So the toy detector, which is used in this software, is such that it assumes that there's a Gaussian width for the energy measurements, and there's a detector factor included to control the relative Gaussian width for momentum measurements. As an example, for example, the other part is the same, but you could say that the detector sigma of which is the energy measurements, it's 1.2 sigma, and for the detector factor, the Gaussian width is 0.9 multiplied by, that of the energy measurement. Then you would get a detector which is toy detector, which has a configuration such as this. And finally, there is a script which can plot the kinematic data directly. So once the script is run, it will generate a set of plots, which are the energy momentum plots for each of this particle after the application of detector effects. Shall not scroll through them. The final example is that the line shape of a heavy mediator. So the inspiration here is to kind of reproduce, like to show in educational environment, like how the Z line shape, for instance, comes out. So as we can see that in the S channel process, for instance, the cross section increases as the energy approaches the mass of the mediator, and like one can reproduce such a line shape with this. So I'll just import a set of packages, including the pymcabc software. We need to define a set of initial momentums at which the collision occurs, and some we need to store the cross section versus the energy at which the interaction takes place. So that is why we are defining these quantities. And then for a set of initial momentum, we will evaluate the cross section, and this is how it is done. And so it takes some time. And finally, we can make plots out of this. So as you can see, as the energy approaches the mass of the mediator, which is in this case the particle A, which is 35 GeV mass. So as we can see at the energy 35 GeV, almost 35 GeV, we can see that the cross section increases drastically. There's a cutoff applied so that it does not go to infinity, which is why we don't see infinity. But yeah, otherwise it can be used in an educational setting to teach a few physics concepts. So as a summary, pymcabc is a toy toolbox for the ABC model, which can evaluate cross sections, simulate scattering processes. It can also generate the decays of heavy particles, and can also apply toy detector effects on the simulation. For more details, you could go through this preprint paper, which includes a variety of examples and ways to analyze this package with uproot and pyroot root. Yeah.
Thanks so much, Ron.
I'd be happy to take questions.
Yep. Let's try and have a couple of them. Quick questions. Anybody? Otherwise, I would ask an previous question, which is, yeah, indeed is a quite pedagogical tool. Are you using it in some for example, in master classes, or where you are based, for example?
Right now, I have not directly applied this, but yes, it can be used, or it can be used, let's say, in an undergraduate setting where we have students who have just learned about the ABC model, let's say from the Griffiths book, and then they could be introduced to HEP software, like how the HEP software or HEP phenomenology works. So that way, this software can be very useful. But I've not yet applied this to any course. Yeah.
Okay, I see. Okay, so oh, there's a hand raised. Jana?
Yeah, there's a question.
So I wanted to ask if this package, which is pymcabc, it can be applied to any process, like if we want to see any decay, or is it specifically for ABC model only?
It is for the ABC model because I have used the amplitudes, like the matrix elements are hard coded in the code at the moment. So it can only be applied to 3 scalar particle phenomenology. Yeah.
Oh,
But
okay.
a similar approach, like if you take the package and if you have another matrix element, you can just, it's quite modular. So you can replace those matrix element and then add your own matrix element. So it should work, should in principle, with some tweaks, you can use it for other processes.
Oh, okay. Thank you.
Yeah, thanks.